Hi everyone. In this video, I want to talk to you about what we can learn about science and how it works, and how it should work, from two philosophers, Karl Popper and Imre Lakatos. So I want to start with a kind of big philosophical question, which is, how do we know what is true about the world? Now, this sounds a little bit like something that maybe a stoner would ask when they're sitting around with their buddies, and it is, but it's also something that philosophers have asked as well. They may or may not have been stoned too. I want to start by framing something called the induction problem, which is something that philosophers have wrestled with for hundreds of years. So induction means deriving a general principle from specific instances. You might have learned about induction in Psychology 202 as something that regular people do as part of just how normal people think about the world. So here's an example of induction. I might say, I ate a heavy lunch yesterday and I felt tired afterward. And maybe this observation, I've had it many times. Maybe every time I can think of that I had a heavy lunch, I felt tired afterward. And so that's a series of specific instances. From those specific instances, I might derive a general principle. I might say, it's not just this time and the time before and the time before. This is a general principle. Whenever I eat a heavy lunch, I feel tired afterward. I might use that to make predictions about the future. Oh, I shouldn't eat a heavy lunch tomorrow because I've got some work to do after lunchtime. That seems like a reasonable, normal way to think about the world. The problem with this is that philosophers have pointed out that induction is not logically valid. It's something we use in our everyday lives. It seems to work, but it's not logically valid, and it can lead us to the wrong places. So a famous example that philosophers talk about is white and black swans. And the background for this is sort of, if you read a philosophy book, a lot of times they'll just throw this example around, but it has a real historical origin. So Europeans for a very long time thought that all swans are white. And the reason was that they only ever saw white swans because that's what kind of swans live in Europe. So the Roman poet Juvenal, for example, in a poem said, "A rare bird in the lands and very much like a black swan," as a metaphor for something that doesn't exist. This became kind of an everyday phrase among Europeans. They'd call something a black swan, meaning that it doesn't really exist. This was the case for a long time, but in 1697, Willem de Vlaming, an explorer from Europe, discovered quote-unquote black swans when he was exploring Australia. And all of a sudden, this assumption that all swans are white had to go out the window. Now, by the way, when I say discovered, I put it in quotes because, of course, indigenous Australians were like, no shit, we've seen black swans all our lives. Okay, but back to the main point. All swans are white is a general principle. It's a broad statement. It's a generalization. The problem with reaching it from specific instances is that you cannot observe enough white swans to know for certain that this is true. Europeans, for hundreds and hundreds of years, every time they saw a swan, it was white. They induced from this using an induction, all swans are white. It turned out that it wasn't true. There's no number of white swans you can observe to prove it's true, but observing one black swan, just one, will prove that it's false. Now, this is a problem for science because scientific theories are general principles. We say things like, what goes up must come down, or people remember the first and last items in a list better than ones in the middle. These are verbal descriptions of theories. Sometimes we describe scientific theories as mathematical laws. They're very general, very abstract. Scientists use observations of the world to test their theories. This is this idea of empiricism that I talked about in an earlier video. But if induction is not valid, how can we use empirical methods to confirm a theory? How can they be useful in science if they can lead us astray? So this is where a philosopher named Karl Popper came into the picture. Popper was a very prominent philosopher in the 20th century, and he was very interested in this induction problem in science and in trying to understand, is there a logically valid foundation for doing science? And what Popper said was, instead of saying, I'm going to figure out how we can do induction validly, he looked at the problem and he kind of leaned into it. And he said, you know what? Induction isn't valid. I don't think there's any way out of this. And so as a result, what Popper said is we cannot prove that a theory is true. And this is something that's been a very influential idea in science. You will often find scientists being very reluctant to use the term prove when talking about their work. Sometimes they'll throw it around casually in conversation. A lot of scientists feel very cautious about using it. We can't prove that a theory is true, and this owes to Popper showing that there's no amount of evidence, there's no amount of empiricism that'll do that. What Popper said is, all we can do is attempt to falsify our theories and see if they survive these attempts to falsify them. So he referred to this as corroboration, trying to subject our theory to risk, to a danger of being proven false, and if it makes it through, then it's been corroborated, but we haven't confirmed it. And so this view within the philosophy of science has come to be known as falsificationism, that what science does isn't prove theories true. What it does is it generates theories and then puts them at risk of being proven false and see if they survive. Now, to get a little bit more into how Popper thought about this, Popper sort of talked about two kinds of statements. These aren't the only kinds of statements a person can make, but these are two important ones in science. Universal statements are general principles, things like all swans are white. Basic statements are reports of observations. They're specific instances, like I saw a black swan in Australia. For Popper, a theory is a scientific theory if and only if it contains universal statements that divide the set of possible basic statements into two sets, those that are permitted by the theory and those that are forbidden by the theory. Let me say that again. Universal statements are the general principles of science. Basic statements are observations. A universal statement is a good scientific theory if there are some things you could observe that are consistent with it and some things you could observe that aren't. So to go back to our example, if we say all swans are white, there are some basic statements that are permitted by this, like there are white swans in Italy, or there are black crows in England. Doesn't have much to do with it, but it's something that's allowed. The black crows broke up in 2015 is kind of a non sequitur. It's a basic statement. It's not forbidden. Observing it doesn't tell you that the theory is wrong. There are, however, also forbidden basic statements. Things like, there are black swans in Australia. This is the basic statement that ended up disproving this general principle to the Europeans. There are gray swans in Nepal would also be forbidden by all swans are white. And there are purple swans in this room right now. Not true, but if it were, that would also falsify the statement. So in addition to this idea of scientific laws having some possible observations, some things you could have observed that would be consistent, and some possible observations, some things you might be able to observe that are inconsistent, beyond this, scientists say that theories are better, theories are more rigorous if they rule out many basic statements. So here's a comparison from a psychology example. Suppose we're interested in the relationship between the physical properties of light, how much wattage is being emitted by a light bulb, for example, and how it appears subjectively. This is something, there's an area of psychology known as psychophysics that's very interested in the relationship between the physical properties of stimuli and our subjective experience of them. Now, one universal statement we might make is the higher the physical wattage of a light, the brighter it will appear subjectively. This is a very general statement. There's some observations that are inconsistent. There's lots that are inconsistent. Contrast this with something from psychophysics known as Fechner's law. Now, you don't have to know what Fechner's law is specifically for this class. I just want you to get a sense of it. If you look at this graph, it tells us beyond just saying, oh, the brighter the wattage, the brighter it feels to us. It, using a mathematical equation, makes a very specific set of predictions about exactly how much wattage will correspond to how much subjective brightness. Among other things, it suggests that as you increase the wattage, it has less and less of an effect. So from going from 0 watts to 100 watts feels like a big difference. Going from 100 watts to 200 watts feels like a smaller difference. When you go from like 10,000 watts to 10,100, you'll hardly notice it at all. This is Fechner's law. So scientists like those more specific theories because there's lots of observations that could prove it wrong. So this is sometimes called severe testing. A severe test of a theory is one in which some result would be very likely if the theory was true and very unlikely if the theory was not true. And notice that the more specific prediction allows for more severe tests. So if I was to do an experiment where I showed people light bulbs of different wattages, 100, 200, 300, 400, 500, and I asked them on a subjective rating scale, how bright are these? There's lots of patterns in the data that would be consistent with that very general, well, the brighter the light, the brighter you experience it. But there's only a few specific patterns in the data that would be consistent with that mathematically specific equation. And so the more specific the theory, it allows for more severe tests. Scientists like that, or at least they're supposed to like it, according to Karl Popper. So Popper's philosophy of science has been very popular among scientists, but there are some difficulties with it. There are some reasons why it wasn't the end of the road for philosophers or for scientists. One of them is an idea known as the Duhem-Quine thesis, a fancy term named after two philosophers. What it means is that every time we do an experiment, we're not just testing the central theory that we think we're testing, but we also have to make a whole bunch of assumptions. And those assumptions could turn out not to be correct. So let's say I do one of these light bulb experiments and I get a result that's not consistent with Fechner's law. Well, I might think, oh, well, maybe I put the wrong light bulbs in the machine, or maybe people weren't using the rating scale correctly, or my subjects weren't paying attention, or something like that. I can always find an excuse to throw away the experiment instead of saying that my prediction has been falsified. And this is a problem because if we can always do this, then we can't have these kinds of severe confrontations with theory that Karl Popper thought we're supposed to be having. Another shortcoming of Popper's approach is because it's only giving us a tool for telling when a theory is false, not when it's true, it kind of leaves out a whole idea of scientific progress. There's no way of telling when science is getting better. All we know is we haven't proven things wrong yet, but there's nothing better about one theory versus another. We can only find evidence against something, not for it. So how do we know when we have two theories, neither of them have been falsified yet? How do we know that one represents more progress than the other? Popper couldn't answer that for us. Another difficulty for Popper is that people have argued this is not what scientists actually do. So historians, sociologists who study scientists' actual behavior have looked at them and said, well, how often do they actually do these kinds of severe, risky confrontations with theory? And it turns out that scientists don't really do this all that often, or at least it doesn't appear to be the case that they're doing it. And yet science seems to be moving along pretty well, and so people have said, well, there must be something missing from Popper's framework because scientists aren't actually doing this, and science seems to be doing okay. So along came another philosopher named Imre Lakatos, who sort of picked up where Popper left off and tried to advance Popper's ideas as well as bring in some of these more historical ideas. So Imre Lakatos tried to reconcile Popper's falsificationist ideas with some of these critiques and with some of what historians who studied scientists' actual behavior said they were doing. And a central idea for Imre Lakatos was what he called a research program. And since he was working in the UK, he spelled it with an M-E at the end. You can see research program spelled like that. So when you see this written down, this is often how people who are talking about Lakatos will spell it. Okay. So Imre Lakatos's idea of research programs is that a research program is a set of theories and assumptions, and it evolves over time. So a theory is a very specific thing, but we might have a whole body of knowledge that's a couple of theories, some assumptions, etc. And he said every research program has what he called a hard core, which is the theoretical assumptions that cannot be refuted without abandoning the program. These are the things that if you let go of these, just everything's wrong, you were barking up the wrong tree, you were going down the wrong path, whatever metaphor you want to use. So within this research program, there's a hard core of things that basically, if they're wrong, then everything's wrong. And then there's a protective belt. These are those additional assumptions that you can change, you can amend them over time without abandoning the hard core. So this sounds very abstract. Let me give you an example. In psychology, there's an area of research on psychotherapy effectiveness. That what psychotherapy means is psychotherapy is a kind of structured social interaction that's designed to help somebody who's suffering from a mental illness or disorder. And the hard core of this area of work is this idea that structured social interactions with a trained therapist can treat or cure psychological disorders. If it turns out that that's wrong, then a whole area of psychology, clinical psychology, would be turned upside down. But around this hardcore, there's a protective belt of ideas that we could change, drop, evolve over time while keeping the hardcore. So we might have evolving ideas about what are the valid forms of psychotherapy. So in the early days of psychology, there was an approach called psychoanalysis developed by Sigmund Freud. This worked a little bit, it didn't work great. As psychologists learned more and more about how to do therapy effectively, now we have something called cognitive behavioral therapy that's much more effective. We were able to change these auxiliary ideas without changing the hardcore that psychotherapy is effective. We might also develop new ideas about, well, we need this kind of therapy for this disorder, that kind of therapy for that kind of disorder. Doesn't require us to abandon the hardcore. So we have an area of research that can progress over time, that can get more and more evolved while still having some coherence, while still having this hardcore that remains the same. So how do you distinguish between whether you're doing good progress and whether you're just making excuses for failed experiments? So Lakatos said there are two kinds of amendments to a research program. Progressive amendments are the good kind. They're where you make an amendment that increases the theoretical reach of a theory and is supported by evidence. So an example of this might be culture match in psychotherapy, where we find that psychotherapy works, but we're finding maybe that it works better if the therapist matches the recipient's culture, or at least is culturally competent, understands the cultural assumptions and values of the person they're treating. And so we might add this to the theory, and so we keep that hardcore that psychotherapy works, but we add it works even better when we have culture match. This is a progressive amendment. It makes the theory better, it expands its reach. Degenerative amendments protect the hardcore without increasing the research program's explanatory reach. So we might have an experiment where we show that the psychotherapy in this experiment didn't look like it worked, and we say, well, okay, sometimes it doesn't work. Maybe it doesn't work in Eugene, Oregon in the middle of winter when allergens are out or whatever. We come up with some reason and it's just kind of ad hoc. It's just making excuses. So Lakatos was trying to, as I said, address this idea that we have assumptions by saying we can divide a research program into the things that have to be true for the research program to be valid and the things that we're allowed to change. And then we can draw a distinction between what kinds of changes make a research program better and what kinds of changes are just excuse making. And it's been argued that this might be arguably closer to what scientists do. So a lot of the day-to-day work of science is just tinkering around a theory, trying to make little improvements. It's not exciting eureka moments like in the movies. This is this idea from Lakatos of sort of, trying to progress around the protective belt. Sometimes scientists try to falsify the hardcore of each other's theories. Rarely they do try to falsify the hardcore of their own program, but this is a rare thing, and Lakatos helps us understand why this is the case. This also helps us understand why researchers don't abandon an entire research program after just one bad result. They keep tinkering, they keep working with the progressive belt to try to see if they can make things progressive, and they wait for the evidence to accumulate. Okay, that's the end of the video. Thanks for listening. Answer some concept questions, and I'll see you next time.